let's talk about the topic for today, which is calibration and analysis of gas detection of multi-component systems. So basically, what we're looking at is, kind of breaking it down to its essence. You have a gas detector, and the gas detector is giving you a value. It's going to give you a concentration. Maybe it'll give you a value in ppm. Maybe it'll give you a value for flammable gas detection in terms of percent of LFL. So the detector is purporting to give you a concentration, but the concentration that the detector is giving you and the actual concentration of the gas might not be the same, especially if there's a discrepancy between how you calculate it or how you calibrate it and what the actual leak is. And things get really complicated when you release a mixture of gases, or your calibration gas and the gas you're trying to detect are different. So we're going to talk about some of the fundamentals. So we're going to begin a little bit with, well, how do these gas detectors actually make their measurement and convert that concentration to an electric signal? And I'll talk about the two most common types of point gas detectors, which would be the catalytic bead and the IR absorption. And then I'll talk about the calibration process in terms of a defined sample gas. So most of the time, you're going to be calibrating based on methane. Methane is a sample gas that is very frequently provided by your equipment vendors. And you can get bottles of very precisely controlled concentrations of that gas in air that you use for your calibration process. But if you calibrate based on methane, but you're actually trying to measure propane, how does that affect the measurement? Because it's not a one-to-one correlation. You can't just say, well, this gas is flammable, that gas is flammable, we're all good. No, that's not going to be the case. And I'll show you what to do with that. So we'll talk about how the actual gas concentration changes or varies from the apparent measurement and how you can deal with that. Now, when you're doing your designs of your gas detection systems, you need to think about what sample gas you're using to calibrate your detectors versus what you want the operators to see in terms of a measured value. And I'm going to start out with this. I'm going to repeat it many times over the course of the conversation. I am going to end with the fact that you need to tightly coordinate your discussions with your equipment vendor. If you explain clearly to your equipment vendor what you're trying to do, they will get you the right calibration gases. They will tell you the right settings. And in a lot of cases, this information is proprietary. So a lot of the stuff that I'm going to be showing you, well, they'll give it to Kenexis, but they might not give it to you because it's sensitive information that can be not necessarily misappropriated, but used the wrong way. So that's kind of the starting point. That's what we're going to cover in this webinar. Okay, so there are a wide variety of different types of gas detectors available. The two big dogs are going to be, number one, the catalytic bead. And catalytic bead is probably the most common. It's the most cost effective, but you're going to see that there are some limitations in that they can get poisoned. They need to be recalibrated frequently. Coming in at number two in terms of popularity is going to be the infrared absorption, where you're basically sending an IR beam out and then bringing it back in, receiving that IR beam, and looking at what frequencies in the IR spectrum have been absorbed to use that to kind of correlate what is the concentration of gas that I'm seeing based on that infrared radiation absorption. Okay, those are the ones that I'm going to talk about a lot today. Those are the most common ones, especially for flammable gas detection. Toxic gas detection, you're going to end up looking at other types of technologies that you can think about similarly in how you do the calibration. Excuse me, how you do the calibration and what sample gas you're using. For toxics, this whole discussion is not as relevant because for toxics, you're generally going to use a calibration gas and your target gas are going to be exactly the same thing. So if you have detectors that are trying to detect hydrogen sulfide, you are going to use hydrogen sulfide as your calibration gas. It's not like we are like, well, I'm going to calibrate based on ammonia, but I'm trying to detect H2S. Well, it just doesn't work that way, whereas it is very common for the flammable detectors. So some of the detector types that you would use more primarily for toxic are going to be electrochemical cells, metal oxide semiconductors. But we're not going to do a deep dive into that because usually you're not going to use those approaches to detect flammable gases, which is our primary concern here. There are even more, a wide variety of detector types. There are multiple different types of laser detectors, which kind of works similarly to IR in that you're sending a beam out and looking at how the beam has changed when it comes to the sensor. Sometimes you're going to look at frequencies that have been absorbed, or sometimes you're going to look at something called the harmonic overtone analysis. And even there is kind of an up and coming interest in gas cloud imaging. So we're going to use cameras and LiDAR type technology inside the cameras to try to see gas clouds from an image. But again, today I'm going to focus on catalytic bead and infrared absorption. I'm also going to focus on point detectors, but point versus open path. In terms of the IR detectors, it's just a matter of whether the emitter and the receiver are going to be in the same location as opposed to spread out over a distance. All of the discussion is going to be pretty much exactly the same, regardless of whether it's a point detector or an open path detector. All right, so let me start out, and you know, the intention here is not to be a tutorial on how gas detectors work. But it turns out knowing how the gas detectors work is going to be important in understanding how you're selecting calibration gases and how you're changing your measured value to what the detector is actually going to show. So for our catalytic bead detectors, we're basically taking a platinum wire and encasing that in a catalyst, catalytically treated metal oxide. So there are going to be two beads in a detector. One is going to be the active element. One is going to be the reference element. So the picture on the bottom right-hand side, you see the active element and the reference element. So what's going to happen is if you bring gas in, and we're kind of showing gas coming in from the bottom of the detector. When a gas comes into the detector, if it contains flammable material, then the combustion reaction is going to be catalyzed by the catalyst that's sitting on the platinum wire. So you're not creating a fire per se, but you're causing that oxidation reaction to happen very quickly without having to create a fire. And when you perform that oxidation reaction, all oxidation reactions of hydrocarbons and, well, pretty much everything is going to be exothermic. So you're generating heat. So if even trace amounts of gas go through the cell that has the catalytic bead in it, it will be oxidized and the temperature will increase. And we're going to measure that increase in temperature by the resistance of this platinum wire. So that platinum wire is going to be your RTD, your resistance temperature device. So the temperature changes the resistance in the RTD. And we're going to have a resistance that we're measuring in the active element that has the catalyst. And there's going to be a resistance measurement in the reference element. And the difference between those two resistances is going to be correlated to the concentration of gas. Now, when I do this, I'm going to use a reference gas to do my calibration. So if I want to measure something like a percent of LFL. So if I want to go into alarm at 50% of LFL, that's my gas concentration. I'm going to want to have a calibration bottle, a bottle of gas that is 50% LFL of methane in air if I'm looking to measure methane. And then I will put that reference gas directly into the detector and see what output is being given, and then use either set screws or heart communications, however I'm communicating with the device, however smart the device is. I'm basically telling it that when I see this differential resistance, this is what concentration that means. Okay, now everything that I just told you is going to be based on the gas that you're giving it. So a certain 50% of LFL of methane is going to generate a certain amount of heat in the combustion reaction. The carbon gets converted to carbon dioxide, the hydrogens get converted to water. That's going to release a certain amount of energy. Well, if instead of methane, I put in ethane or propane, effectively more reaction is happening, so more energy is being released, so the temperature will be hotter. So what that tells me is that if I calibrate based on methane, but I'm trying to measure ethane or propane, the measurement will actually be lower than actual. So that's kind of, in the world of gas detection, that's going to be a dangerous failure. So how do I deal with this issue? Well, before I tell you how to deal with this issue, let's talk a little bit about strengths and limitations of the catalytic bead. Again, the workhorse of the industry, its strengths are that it's going to be able to detect anything combustible, and that includes hydrogen, which has no carbon. So you can detect literally any gas that will combust. It's going to be very accurate, especially right after calibration. It's got a decent service life of 3 to 5 years. Now, why would some people choose not to use the low-cost proven alternative? Well, number one, that catalyst can get poisoned. So if you expose the catalyst to certain chemicals, possibly sulfur. I don't want to go give you a list of poisons because it's going to vary depending on who your vendor is and what catalyst they're using to do this. But there are chemicals that might be out in your plant that will deactivate the catalyst and prevent it from working, which is a dangerous failure because if you have a gas and the catalyst is poisoned, it's going to either show you a low concentration or no concentration at all. Also, frequent calibration is required. A lot of people will do this on a monthly schedule, and that's because there's a degradation over time. Those of you that are attending from the refining industry understand a concept called coking, in that when you're combusting or heating even a hydrocarbon material, you could end up creating elemental carbon or coke. And as that coke sits on the catalyst, it's going to prevent air from reaching the catalyst and kind of decrease its effectiveness. And you can account for that by recalibrating it, but it's something that, depending on the background atmosphere, you might need to do very frequently. Also, down at the bottom here, you're going to see a flame arrestor is something that's very common, where, I mean, this actually just looks like a filter as opposed to a flame arrestor, but I digress. I'm not here to teach you about different equipment vendors' options, but the small holes through which the gas needs to travel to get to the sensor cell can get plugged, whether it's a flame arrestor or just, any kind of filter that is there to protect the cell can get plugged up and prevent the device from working. So those are some strengths and some limitations. Now, let's get into the heart of what we came here to talk about, which is how you address calibration gas versus a different gas. Now, what you're looking at here are excerpts from a spreadsheet, and I'm going to warn you right now not to use any of the data on this slide, because the data may or may not have been modified from the equipment vendor that presented it to me. And I'm not going to tell you who the equipment vendor is, and the data from each model of each vendor is different. So I'm going to tell you how this gets done, but what you're going to do is you're going to talk to your vendor and get the information directly from your vendor. Okay. So I'm showing two lines out of this spreadsheet, one for butane and one for methane. But overall, what are the columns on the spreadsheet? Well, we have a chemical name, we have a chemical formula, we have a concentration of gas that is presented in percent of LEL and methane. And this information is what you're going to use to get data on the responsiveness of the component. So what you'll see first off is that the set points are going to be different. So even before we talk about how the detector responds, look at the difference between methane and butane. So for methane, 50% of LFL is 25,000 parts per million. But for butane, 50% of LFL is 9,500 parts per million. So right out of the gate, if you're calibrating based on percent of LEL or percent of LFL, that's an actual different concentration when you start looking at parts per million. So you have to understand that the parts per million is kind of the truer representation of what you're measuring, and the percent of LFL gets contrived off of that parts per million. So, step one, if you're calibrating at 50% of LFL for methane, that's a 25,000 ppm concentration of your gas, which is going to be completely different when you're looking at butane. So that's item number one to remember. Those ppm values and even the percent of LFL, the lower flammability limits are going to be different depending on what species you're looking at. Okay, so given that though, let's look at the next variable, which is going to be the measured value. Ultimately, the measured value is going to be in millivolts. So we're taking, and there's going to be a bridge in the electronics for the device where, the RTD for the reference and the RTD for active are on different sides of the bridge. You're using the bridge to get a differential, and that's going to be in millivolts. So if I am measuring a 15%, I'm sorry, a 50% of LFL of butane, there is a certain millivolt measurement that is correlated to that. Now, all these numbers for millivolts are going to be based on a brand new device. So this is kind of what they expect for a brand new device coming out of the box in the laboratory. These millivolt numbers I've already explained to you in the calibration process are going to change over time. So the same concentration of calibration gas is going to give you a continually decreasing millivolt signal as your catalyst gets coked up and otherwise gets deactivated. So that's why you need to do the constant recalibration, because that measured millivolt value is going to decrease over time. So now what the equipment vendor has noted is that there is going to be a difference between the millivolt number that you see for your target gas versus other gases. So in this case, 116 is, oh, bear with me, there's going to be more information on the next slide that gets into a little bit more detail. But the same concentration of gas is going to provide different millivolt values depending on what the target gas is. So if you calibrate with methane, you're going to get a different value for butane. If you calibrate with butane, you're going to get a different value for methane. So now, how does that work? How does the calibration of gas versus the apparent signal change the values? So what we saw on the previous slide is that if methane is our calibration gas, it's going to generate a 50% LFL signal at 116 millivolts. So 116 millivolts, again, I cannot stress this enough. Don't use this information. Go to your equipment vendor, because it changes not just on vendor, but also make and model of device. Two different catalytic bead detectors from the same manufacturer could be giving you different numbers. But basically what we're looking at is 116 millivolts of methane is 50% of LFL. 77 millivolts is generated by a 50% LFL of butane in this particular case. So if I'm calibrating a device based on methane, 50% LFL of methane, I'm going to be looking for a different millivolt value. So the 66.38%, that number right here, is what fraction of 116 millivolts 77 millivolts is. So it gives you a scaling factor to set your LFL. So if you calibrate based on methane, but your target gas is butane, you need to multiply your value by essentially 66.38% to get to the correct LFL value. So for instance, if you did use 50% LFL methane calibration gas in this example, that 50% LFL of methane is only going to give you 33.19% LFL of butane. So it is possible to use different calibration gases and still get a correct number. But even though it's possible, your equipment vendor is generally not going to recommend it. We at Kenexis are not going to recommend it. Why are we not recommending that, hey, you could just buy methane and calibrate everything, regardless of what you're trying to detect? If you know you're specifically trying to detect butane, you should be using butane as a calibration gas, because what you're seeing right here is 1 point. And I'll show you this in a line a little bit later, the millivolt response versus concentration is generally linear. It's not ever exactly linear. So be careful when you're using other calibration gases. But what we're showing you here is kind of the mechanism by which you would do it. And also, at the end of the day, I can't tell you what this percentage value that you need to put in to your system is going to be. That's something that you need to definitely go to your equipment vendor for. What I've presented to you is kind of a simple case. So I'm calibrating using a bottle of 50% LFL methane, but I want to present a reading to my operators that is, well, what is the percent LFL of butane? So I kind of showed you that scaling factor, and then I warned you not to do this, but sometimes you have to do it. And the reason why sometimes you might have to do it is if you have multiple target gases. So let's go to a gas plant in an oil refinery. So in an oil refinery, we're bringing our crude oil in, and off of the top of the crude tower, we have a mixture of gases that's going to go to a gas plant. And in that gas plant, we're first going to separate our kind of heavier stuff. So any residual naphtha we're going to knock out. And then we're going to go and we're going to do a depentanizer to remove your pentanes, debutanizer to remove the butanes, depropanizer, and so on. So you're splitting that gas potentially, depending on your configuration, into multiple different gases. So when I place a gas detector out in that gas plant, I don't necessarily know where the leak is coming from. It depends on which piece of equipment is leaking. It depends on which way the wind is blowing. I might be detecting a leak from the demethanizer. I might be detecting a leak from the depropanizer. I don't really know. So you're kind of in a pickle when the gas that you might be detecting, it might be this, it might be that. So if you have multiple target gases, what do you do? Well, we in the safety business, we're conservative. We always do the worst case scenario. So we're going to go back to this table, and we're going to look at all of the target gases and figure out which target gas is going to give me the highest apparent reading. And basically what that means is that if, let's say, butane is giving you the highest apparent reading, but there's a methane gas cloud, it's going to show you a percent LFL value that's higher than it actually is. And that's what we in the safety business do. So figure out which of your target gases is going to give you the worst case and do your calibration based on that worst case. So that's the discussion for multiple target gases. But even worse is if you have a mixture. Now, mixtures, you could do it a couple different ways. But what would we at Kenexis recommend? We at Kenexis recommend what we just told you for multiple target gases. So these are two different concepts. For multiple target gases, it might be methane, it might be butane, it might be propane, but it's one of them. In this case, I've got a mixture. It's 50% methane, 30% ethane, and 20% butane. So I have a mixture that I'm trying to detect. One of your options is to try to get that witch's brew concoction created as a calibration gas. Not something that people will normally keep on the shelf. probably a very expensive thing to try to accomplish. So not really feasible for most people to get a calibration gas that actually is a mixture of the same mixture that they would be releasing. The other option then is to just basically look at, well, what is in this mixture that I'm releasing, and do the same thing you did in the last bullet point, which is figure out which of these is going to give me the highest apparent LFL, the most conservative, and calibrate based on that. And in this case, if you have a mixture and your bad actor in the mixture is butane, you probably want to calibrate based on butane. But again, now I'm getting, different layers of conservatism. The other thing that you can do is calculate a value based on partial millivolts. What do I mean by that? So what you could do is you can take mole fractions. So let's say I have a mixture that is 50-50 butane and isobutane. What I would say is that my millivolt value is going to be 0.5 times 77.001 and also 0.5 times 81.003. Add those together to get what millivolt value should be generated by that mixture. So we're kind of using the concept of partial pressure, looking at each species and its mole fraction to generate a partial contribution, add all the partial contributions together to get a total contribution. This is a little bit less conservative, a little bit more aggressive, but it might be appropriate for what you're doing. But again, now we have another complexity in that, well, I know what my partial millivolt is. And if you go back up here, so you use this same kind of concept. This right here is what you would put in for your partial millivolt value. And then, you multiply that against your calibration gas to figure out, again, what your effective LFL is. So that's kind of the process. I know I've spent a lot of time looking at these two slides, but the concepts are fairly straightforward. You're going to have data available to you from your equipment vendor who, again, I know I keep beating this up over and over, but your equipment vendors are excited and happy to talk to you about this. They will run the calculations for you. They will explain everything that I just explained, maybe not in as much academic detail, but the gist of it, to help you come up with what is the right calibration gas and what values you should be setting it for. Okay, so now how does all of this affect gas detection mapping? So gas detection mapping is that process that you use to determine how many gas detectors do I need, where do they need to be located. And if you want more information on gas detection, go to the Kenexis website. There is at least 2, maybe 3 webinars that we've done on various topics related to gas detection mapping. But essentially for gas detection mapping, what we do is we run dispersion models of releases of the gas and see how the release rate, the release elevation, equipment impingement affects what the gas cloud looks like. And we'll get results that look like what you see on the screen right now. So on the left-hand side, you kind of have a side view of the release. The material is released here at about 1 meter. And then you can see that this is for a dense gas. So we have propane, which is a dense gas. And you'll see how from the release point, the gas sinks down toward the ground and spreads in a dense behavior. And then that same propane release there's something called a footprint, which is the top-down view looking at this gas release. So when we're doing gas detection modeling, we're going to run these dispersion models, and we're going to figure out, well, what is the width of this gas cloud at its maximum width? What is the length of the gas cloud from the footprint? And then we're also going to get this thing called the offset, which has to do with elevation effects, in that the detectors are placed at a different elevation from where the release occurs. Thus, there's going to be a gap on where the release is and where your footprint shows up. So when we're doing our dispersion modeling for our gas detector placement, we need to know, well, what concentration am I going to run my dispersion model out to? And usually when you run your dispersion models, you're going to be looking at a single species. So here in these pictures, I'm showing you the concentration of methane at different distances from the release point. When you have a multi-component mixture, you're going to need to use these rules to determine, well, what is the actual concentration that I can detect? So the end point for our detection modeling is the set point of your detector that you're going to put into the gas detection mapping program. That's what you need to tell your dispersion modeling people when they're doing this. So if, again, I'm measuring butane, but I'm using methane as a calibration gas, when I run this dispersion model, I need to know what concentration of butane is going to cause that detector to go into the alarm state. So these decisions on calibration gas, they have a lot of tentacles and they go everywhere. It's not just the act of calibration, it's understanding what your sensor is showing to your operator, and even the engineering process that determined where your gas detectors were going to be located. Okay, so let's move on really quick to the next point of discussion. Everything that we talked about so far is not limited to, but it's focused on catalytic bead gas detection for flammables. The other popular technology is infrared gas detectors. So hydrocarbon gases are generally going to absorb infrared radiation at around 3.4 microns. So I don't want to get too deep into quantum mechanics or physical chemistry, but the frequency at which the IR radiation is going to be absorbed is going to be a function of your different excitation states of your electrons, and it has a lot to do with your bond lengths. So whatever actually causes it, by empirical measurements, you're going to know that the absorption of hydrocarbon gases is going to be happening around 3.4 microns. So when we're using an IR detector to detect flammable gases, hydrocarbon gases, and it is going to be hydrocarbon gases, that's going to be a limitation that you'll see, the presence of the hydrocarbon gas is going to reduce the transmittance of IR radiation, because the IR radiation gets absorbed by that carbon-hydrogen bond and it excites it into its next quantum state, effectively, is what's happening. Okay, so what we're doing in the detector is we're comparing the measurement of infrared radiation that is coming back to the detector against the amount of infrared radiation that was sent out of the detector, and the difference between those relative frequencies, or the amplitude of those frequencies, is going to get converted into a 4 to 20 milliamp signal. Now, once again, we are going to calibrate to a reference gas. So we're going to take that IR conversion, or the IR absorption, and convert it into a signal that is going to be kind of tempered and smoothed out based on the reference gas. Now, there are things that are going to impact the amount of absorption that vary from detector to detector and vary over time. So things like the thickness of the lenses that the light has to go through, the intensity of the generation of the light beam. Those are things that will all vary over time. And are going to vary depending on the manufacturing process, which is why you need to do calibration instead of just taking it out of the box and assuming it's going to work. But one of the strengths that we'll see of the IR gas detectors is that this does not change a whole lot over time, which means that your calibrations are going to be less frequent and less impactful because the absorption doesn't change that much over time. So let's go ahead and look again at the IR strengths and limitations. And also on this slide, you can see a little bit more information about how these devices actually work. Now, if you're really interested in knowing how these devices really work in a little bit more detail, I'd recommend going to the ISA EC56 training class on fire and gas detector mapping, which is going to talk not just about fire and gas detector mapping, but also the technology of the devices and how they work. So you see here in these images that you're going to have an IR source over here. It's going to send beams, and the active beam is going to go through your gas, but your reference beam is not going to go through the ambient air. So you're going to be able to measure the difference again between active and reference in terms of absorption. You can see that again here. We've got our IR source, and you're going to be able to deflect the beams between reference and analytical. Okay, so strengths and limitations. Number one, low maintenance. You don't need to calibrate this as much because there's not as much that changes over time based on the technology. There are no poisoning issues, so you can't expose this device to a gas and have it kill it off and make it not work. The other strength of the IR devices is that even though you can have a point detector, there's no reason that your source and your detectors, sorry about that, need to be in the same location. So instead of having them inside one enclosure, you can have one source at one location and then your detector tens of meters away and shoot the beam across open space and see kind of have like a greater coverage because any gas cloud that goes through that beam is going to be detected as opposed to the gas cloud having to come to the detector itself. Now, limitations. Number one, if you're not measuring a hydrocarbon, I won't tell you it's impossible, but I will tell you that it's more complex. And the reason that it's more complex comes back here in that, your manufacturer, for the most part, is tuning their device to look at a certain frequency range, and that frequency range is based on hydrocarbon gases, looking at that carbon-hydrogen bond. If you have a different bond, an oxygen-hydrogen bond or a sulfur-hydrogen bond, those bond lengths are different. They have different characteristics. They're not going to absorb the same amount of IR radiation at the same frequencies. So this is something that if you're not looking at a hydrocarbon gas, you need to coordinate with your manufacturer. Now, I know, for instance, right now, with the green energy future and a lot of push to use hydrogen in energy storage and energy transmission applications, that a lot of people are interested in hydrogen gas detection. And I know that a lot of equipment vendors have tuned these IR gas detectors to be able to detect hydrogen. And that's a matter of understanding what frequency should we be looking at and how do we detect an absorption at that frequency. So if it's not a basic hydrocarbon application, you definitely want to coordinate with your equipment vendor. The IR items are going to be less accurate with mixtures because, as opposed to kind of that, that partial millivolt approach, which I'll talk about that again with IR, but with different species in a catalytic bead, they're all combusting, and you can get a relatively good handle on the difference in heat release between a combustion of ethane versus a combustion of methane. Things are a little bit more straightforward. Whereas the amount of radiation absorption of methane versus radiation absorption of ethane or ethene or ethylene, those are going to be more different, and the relation between them is not as obvious or direct or linear as just looking at the heat of combustion that they generate. Okay, so here's another example of information that your equipment vendors have that they may or may not be willing to share with you. And this is for a device, an IR absorption point gas detector that's been calibrated to methane. So for methane, and you'll see that methane is your blue line here. So it's this guy right here. And as you would expect, from 0 to 100% LEL is 0 to 100% of your full scale reading, because that's exactly what you calibrated for. And then you're going to see that different gases are going to give you different values. Now, what you'll see is that in some cases, they're roughly linear. So if I go down here and I look at ethylene, so this bottom line here is ethylene, that a measurement, so if you calibrate to 100% methane, but you're trying to measure ethylene, that 100% methane is actually only 35% of LFL for ethylene. But you'll see that you have a pretty straight line here. So just doing a scaling factor is going to give you relatively good results. Whereas if you compare that against this line here for pentane, this line's a little bit wonky. It's not a curve, but it's a little bit wonky. And even this line here for 1,3-butadiene has kind of a couple wonky points. So we lost our linearity there, and we lost our linearity here. But between 10% and 90%, it still looks pretty linear. So again, you're going to need to do the same thing that I talked about on the previous slide in terms of that calibration point. So if you're calibrating to 50% methane, but you're trying to detect ethane, your values are going to be dramatically different. So a 50% reading from an ethylene that's calibrated this way is only actually 10%. So you're going to need to go back, get your scaling factors, and basically say, if I'm putting 50% methane in as my calibration gas, what value am I going to see? And looking at this, there's no equation anyone's going to give you. This needs to be done empirically. This needs to be done by the equipment vendors, and the equipment vendors are going to present this information to you, which brings me back to that, again, most important point of discussion. Please go to your equipment vendors. While they might not give you this graph that has all the data for everything, they'll give you the information that you need to have for your application. So please coordinate with your equipment vendors. Okay, so in summary, what did we talk about? Gas detectors have a measured value. It's going to give you a ppm concentration. It's going to give you a percent of LFL concentration, especially when you're looking at flammable gases. Now, the measurement that it's going to give you is based on a calculation and a calibration, because you're not actually measuring a ppm value of the gas. You're measuring, in the case of catalytic bead, a millivoltage. In the case of IR detectors, an absorption of radiation. So you need some sort of mechanism to scale what you actually measured to what you want to read. And if your calibration gas is different from your target gas, there's another step that says, well, I'm calibrated to 50% of LFL of methane. What is the value now that if I was presenting ethane instead, that this device would be reading? That needs to show up in your calibration sheets, in your calibration procedures. And really, when you're setting up your calibration sheets and your calibration procedures, you need to make all this abundantly clear. Don't assume that the technicians just know. You need to list out the type of gas they should be calibrating to, the type of gas that they're actually trying to detect, and all of those calibration factors. Don't assume, make everything very clear. So when your target gas and your calibration gas are different, correlate the measure value based on test data. Your equipment vendor has this test data. When you have multiple target gases present, your safest, most conservative thing to do is use the worst case, or have the detector show an LFL value for whichever component is going to give you the highest LFL value. When you have mixtures, use the worst case, or you can do a summation of partial values to do the calibration. The worst case is going to be more conservative. The partial values requires a little bit more work, well, actually a lot more work, and it's a lot more aggressive. And again, we'll end with my big all cap statement. Please work with your equipment vendors to understand your situation and get those different calibration values. Any questions? But in the meantime, I guess I would kind of stress that there are a lot of operating companies that are trying to save money by always calibrating to methane, regardless of what they're actually trying to measure. And that's, as I've showed throughout this training class, that's possible. You can set that up, but you have to understand that this is a human factors nightmare for your technicians who are going to be doing the calibrations, because the technician who's doing the calibration needs to know, okay, I only have one type of cal gas, but depending on what this detector is supposed to detect, I need to change what my reading is as a function of that gas. So I can't assume that 50% cal gas means that my detector should be showing me 50%. It's going to change depending on what I'm trying to actually detect. And that can basically, I would say you're setting up a human factors failure that could be dangerous. I think someone had a question.
I'm asking why we just calibrate gas according to our products. For example, we use gas detectors for protecting gasoline, kerosene, naphtha, and it is a mixture of gases that almost the same all over the world. Why the manufacturer doesn't calibrate it just to it, not to separate components?
Well, that's an interesting question. So, and I will have to possibly follow up with a LinkedIn post or a newsletter about this. I would be very interested to learn a little bit more about what some of the equipment vendors have done for calibration of mixtures. And now I'm going to set up some meetings to do exactly that. But you have, so let's say naphtha. Naphtha is going to be, a lot of C5s, a lot of C6, a lot of C7. But the concentration profile is going to vary from one refinery to the next, but how much it varies in terms of that millivoltage. So let me put this away and then bring that slide back up. Bear with me for a second. So kind of looking at these values, you see that butane is 77 millivolts, methane is 116 millivolts. That's a pretty dramatic difference. But how dramatic would the difference be for naphtha from refinery A and naphtha from refinery B? I honestly don't know the answer to that question, but I will follow up with MSA. I will follow up with Detronics to get their input on that. So that's something I will have a future website post because I don't have that information at my fingertips. That's an interesting question.
What are the reasons we do not have combined fire and gas IR detectors rather than separate gas detector and fire IR detector?
Okay, good, great. That's an interesting question. I mean, IR is after all, but they are completely different. So for an IR gas detector, you are using a lamp, an LED usually, but you're using a lamp of some sort to create a custom infrared light signal. So the detector is creating the light signal, sending it out, bringing it back, and measuring what comes back. For an IR fire detector, it's the fire, the heat source, that's generating the infrared radiation. So number one, an IR fire detector doesn't create infrared radiation. It's only receiving it from the fire. Number two, the frequencies of detection are different. So for a fire detector, there is a certain frequency of radiation that gets generated, going back to quantum mechanics and physical chemistry. When an IR bond is very excited, moving very rapidly because the temperature is very high, the molecule will want to cool itself off by emitting a photon, and that will slow down the radiation. We call that a radiative cooling. And the frequency of that IR signal is going to be different. So the radiation generated is going to be at a different frequency from the radiation that's absorbed. So that's item number two. Item number three is location. So for an optical fire detector, I'm going to want the detector up and away from the equipment I'm trying to monitor. Whereas a point IR gas detector, I want that right in the process where I expect the leak to occur. So there's 3 reasons why you wouldn't want to put the same device for both of those purposes. I mean, there might be a little benefit in the fact that an IR gas detector is measuring IR absorption, or measuring an IR signal intensity, and an IR fire detector is measuring an IR detector intensity. But there are a whole lot of other reasons why it doesn't make sense. So I don't think that's coming anytime soon. Is there any way to account for the worst case scenario being significantly more sensitive than other scenarios when looking at target gases? So if the alarm is set off at low concentrations for other target gases, well, there is a way to account for it, but you're not going to want to hear it. Nobody wants to hear it, and that's to use different detectors. So if your species A is firing off at 30 millivolts and species B is firing off at 200 millivolts, you're going to get an alarm for one species when the other species is trivially low. The best and the example of this that probably you would see the most in the process industries is not necessarily for flammable gas detection, but for H2S. So the amount of H2S in a released gas could be extremely low, way lower than the parts per million of methane or flammable gas that'll cause your detector to go into alarm, which this discrepancy in set points is why you generally want to have an H2S detector and a flammable gas detector, because they become hazardous at such wildly different concentrations that you can't use one detector for both purposes. So unfortunately, the answer is more equipment and separating them out. Okay, next question in the chat. You have shown a gas cloud dispersion, which is your point of view regarding the generic use of factor of influence. Let's say 5 Demeter gas. Okay. Field of influence. Okay. What I showed you for gas detection is okay. The whole concept of fire and gas mapping is very complex. It's a 3-day training class to even get the basic information. There are 2 types of gas detection methodologies or gas mapping methodologies. One of the methods is called geographic or volumetric coverage. The other approach is called scenario coverage. So what you're referencing, the field of influence, or in the Kenexis fire and gas mapping software, we would call it the critical gas cloud size, is a value that is a factor that's used in a geographic coverage calculation. So basically what you're doing in that is you're saying that if I have a detector in a certain point, if I have a spherical gas cloud whose center point is a certain distance away from that gas detector, the gas cloud will be detected. Okay, that's a very simplified approach. That's a very geometry-only approach. And while it is still commonly used in the process industries, we at Kenexis do not recommend using geographic coverage because it's overly simplified. Geographic coverage, which basically says there's a certain distance away from the gas cloud that I'm going to detect a gas leak. That's bunk. That's simply not true. What you're actually saying is if I have a spherical gas cloud a certain distance away from that detector, I will be able to detect it. Well, the problem is the only time gas clouds are spherical is if they're inside a balloon. And also this the scenario coverage approach doesn't consider release orientation. It doesn't consider the frequency of where the releases are coming from. It doesn't consider weather effects and dispersion effects of where the gas clouds are going to. So even though our software allows you to do geographic coverage where you're looking at this field of influence factor, we always recommend the scenario coverage approach, where in the scenario coverage approach, you're not going to just say, okay, well, I'm going to assume that if my gas cloud is in, if my leak is within 6 meters of this detector, I'm going to detect it. We actually run the dispersion models to see where the gas cloud's coming from, where are they going to, how frequently are the gas clouds occurring, and all of that goes into the second approach, which is scenario coverage. So both of those approaches are allowable according to the ISA 8407 technical report. But the scenario coverage is dramatically better. You're going to get much better coverage with much fewer detectors using scenario coverage. So all those gas clouds that I showed you have no impact on the critical gas cloud size or the field of influence. Okay, actually, before I leave that field of influence, most of the time when you're using a field of influence or a critical gas cloud size because you're using scenario coverage, there's always a question of how big should that be? And the answer to that, how big it should be related to gas clouds that you can generate from your particular plant. And the concentration of your gas should have some impact in there. If you're trying to figure out an appropriate field of influence or critical gas cloud size for a mixture, I can probably put together some ideas for you on that, but it's not something that I've really thought about recently. I'd have to give it some more thought. Okay, next item, can a ceramic catalytic based flammable gas detector calibrated with methane be used for hydrogen? Short answer is yes. The same factors are going to apply. So you need to go to your equipment vendor and say, I'm trying to measure the concentration of hydrogen. I'm calibrating based on methane. What is that percentage that says this is my calibration gas, this is my target gas? What percentage should I be multiplying for when I give my calibration? So it's just a matter of getting that number from your equipment vendor. And I expect that your equipment vendor will probably try to discourage you from this. They will probably encourage you to use a hydrogen calibration gas. But you need to have a conversation with your vendor. But just from a pure scientific instrumentation and control perspective, yes, you should be able to use this approach to do exactly what you're asking about. Thank you for attending, and I'll let Chris wrap it up.
Thank you,
Thanks
Ed.
for the excellent presentation, Ed, and thanks for all for joining us today. We value your time and truly appreciate it. We'll conclude the webinar at this point.
Thanks, everyone. Have a great day.